All right, so we're in search of the interval of convergence for this next example. So we're going to use the ratio test. Okay, and there it is, the setup. Let's do the cleanup. Appears 2 to the n is going to cancel with 2 to the n down here, leaving 2 to the first power. And x plus 1, quantity x plus 1 to the n is going to cancel with quantity x plus 1 to the n, leaving just a quantity x plus 1 to the first power. So we're in search of the interval of convergence, but we need to find the radius of convergence first. And then everything's based off the center. And although not mentioned at the beginning of this, the center here is going to be -1. All right, let's clean this up. All that remains on top is it's x plus 1. Oh, and all that remains in the denominator is 2. Okay, I'm going to go ahead and pull out the quantity x plus 1. And that just leaves a half. So that limit is going to be a half. So if this limit's a half, I'm going to pull it in front, and I'm just going to say, okay, my answer to this limit question is 1/2 absolute value of x plus 1. Okay, well, remember we're in the ratio test, and for the ratio test, we want to look for, where the radius is less than 1, equal to 1, or greater than 1. If the radius is less than 1, then our series converges. If it's equal to 1, the ratio test is inconclusive. If it's greater than 1, then we know it diverges. Okay, well, right here, I'm at a point where, okay, on this, with the ratio test, I want it to converge, and so I'm going to force it to be less than 1. So this expression right here, okay, so if I can find a value for x, add it to 1, find its absolute value, multiply by half, and if that value that I put in for x allows this output to be less than 1, then this power series will converge. Okay, I have a little bit more work to do. What I'm going to do on this right here is I'm going to multiply. I want to isolate the absolute value of x plus 1. I want to multiply both sides by 2. So the absolute value of x plus 1 is less than 2. And that's important that we do that we isolate the absolute value of x plus 1. Okay, remember the center is -1, and we can tell that from this expression here too. If the center is -1, then we can come up with the interval of convergence as well. So right now we know this results in us having a radius of convergence of 2. So thinking about the interval of convergence, if my center is -1, I need to stay within 2 units. So that's going to put me at, if you think about a number line, an interval of convergence of -3 to 1. Okay, and don't forget we have to test endpoints. Let's see if these values, -3 or 1, allows our power series to converge. So let's let x be -3. Okay, if x is -3, I'll put that in there, but let me get the rest of the nth term. If x is -3, then that becomes negative, what, 2 to the n? Okay, so you might want to do a little bit of algebra on this. If we're trying to think of all the different series tests for constants, because this is now a constant, it's not a power series anymore, it's a constant series. If we think about all the different tests, we might want to do a little bit of algebra work first. I'm looking at the numerator, I'm looking at this part of it, this factor. Oh, you're kidding me. All right, what we can do is we can think about what's inside here as a product. Okay, let's think of it as -1 times +2. All right, so inside here we can think of that as -1 times +2. Okay, so, and that's to the power of n. So, and then I can apply that power, so what's going to happen is this. It's just slow. We have -1 to the n times +2 to the n, all over 2 to the n. Okay, well, right here, -1 to the n times -1 to the n, if you think about what's going to happen there, same base, add the exponents. What's -1 to the 2n? Well, this is always going to be a positive exponent, so that means that this is always going to be positive, so they really kind of create a positive situation here and undo each other. Okay, look at what's left. We have 2 to the n over 2 to the n. So this series really, if you do a little bit of algebra on it, is going to simplify to just 1. I knew that was going to happen. I don't know why this pen's, it's had time off, and then it just reappears. So if this is 1 right here, then this is equal to, let's see, the diverges. Sorry. So if we have this sum right here, what we can say is, by the nth term test, find the limit of find the limit of 1. Well, that goes to 1. So we're going to say that this series diverges by the nth term test. I don't know where everything's going. Okay, so we don't want to include the -3 with the bracket. So now let's test x equals 1. Okay, everywhere you see x, replace it with 1. So that's just 2 to the n. Those are going to cancel. I'm trying to write down, I guess if I be patient, maybe it'll all show back up. -1 to the n. Oh. So if I were to find the limit of the nth term, or find the limit here of this expression as n goes to infinity, okay, my answer is either going to be, when I find this limit, +1 or -1. Well, that's not leveling off. That diverges. So finding the limit of the nth term, we saw that this diverges by the nth term test. Neither one of the endpoints are going to be included. So that wraps up finding the interval of convergence for this example. Okay, maybe I'll have better luck with this last example. Let's find the interval of convergence for this one. Okay, the setup of the ratio test. Now the simplification. Pull out the absolute value of x. Notice that if you were to equate this with a function here, that this is going to be a rational function, either using L'Hopital's rule or knowing your rules of exponents, we can see that the limit as n goes to infinity here, okay, gives us n squared over an n squared, so that's just 1. So this is 1. So 1 times absolute value of x is just x. And so if we want to force this power series to converge, okay, it has to be that that's going to happen at values less than 1. So our radius of convergence is 1, and because the center here is 0, we know the interval of convergence goes from -1 to 1. So we just have to test 2 endpoints. So the radius of convergence is 1. Then so far, without doing any tests, we know what the interval of convergence is. Okay, so we'll do a test on both endpoints to see if that produces series that converge. So let's test the endpoints. Okay, go to the original problem, the original series, and everywhere you see x, replace it with 1. So we have 1 to the n, which is just 1, 1 over n squared. Ah, nice. It's not behaving. Okay, so this is, oh, was this -1? We're letting x be -1. My apologies. Let's let x be -1. So I have -1 to the n. All right, so remember our p series for our terms, they all have to be positive. So we're going to have to use the AST for this. So let's go through the two-step process there to see if this is convergent by the AST. All right, step 1 is the limit of the nth term when we just consider the absolute value. Is that positive? Part 1, this limit is a p-series, okay? Or actually, we're just finding the limit. My apologies. So as n goes to infinity, this is going to go to 0, so part 1 is satisfied. Oh. Okay, and then let's look at the comparison of terms as well here. Is that always less than 1 over n squared? It certainly is, because this denominator is larger, meaning the value is smaller. So both parts of the AST are satisfied. So that tells us that this series of constants will converge when x is -1. So we're going to come back up here and we're going to make this a bracket. So now let's test the positive one. Here we're going to have 1 over n squared. So if we're looking for convergence or divergence, we see this as a p-series, and it's convergent, where the power is greater than 1. Okay, convergent, we know that. So you'd come up here and change this endpoint right here to have include a bracket. Okay, a little bit of pain with the pen. I don't know, try and figure it out, but hopefully you got the idea of interval of convergence and how you have to first go through the radius of convergence, and then you have to test the endpoints, and that's where our past series tests come into play.